Okay, gang. So here's one of the 3 or 4 big reactions we're going to do when we're talking about alpha carbon chemistry. And it's called the Aldol reaction. And you can do this in both basic and acidic environments. But this video is just going to talk about the basic environment. And then the next video, we're going to basically touch up what happens in the acidic environment, because this is basically going to cover most of the concepts here. So first kind of tip off, right? We're in a basic condition. And here's kind of the pieces you need for an aldol reaction. You need a carbonyl, kind of like the equation of things you need to add together, and an enolate, right? You need these 2 things. And then that will give us an aldol product. And based on one factor, you can have it, the aldol product will look, a little different, but we're going to talk about that once I throw up an example. Just a quick aside, if the chapter before this, the unit before this with carbonyls, if that was based solely around mechanisms, then if you want to make this analogy, everything we're going to do here is kind of based on relationships in the final product, and you'll see what I mean. So let me throw up a quick aldol reaction for you, okay? So let's just say I have this carbonyl, and let's just say I was to, I'll actually just draw the enolate form for you guys. Let's say we made this carbonyl into an enolate, so it looked like this, right? It's a symmetrical carbonyl, so it doesn't matter if I make my enolate to the left or to the right, but I'm going to make it to the right. Okay, now I'm going to make a carbonyl, and I'm going to pick benzaldehyde. Okay, let's just take this to be our carbonyl. So I have an enolate, I have a carbonyl. Let's just say I stuck them together just as is. And we know we're in a basic environment because we have negative charge, and we have an enolate, right? Because if we were in an acidic environment, we would have an enol. Okay, here's how the electron flow goes. I'm going to swing these electrons down to reform our carbonyl. Remember, in the last video, I said we're going to be attacking with our alpha carbon. So I'm going to dot and darken him. So once these electrons swing down to reform our carbonyl, the electrons right here are going to come forward from the alpha carbon, and we're going to attack our partially positive carbonyl in our carbonyl piece. Nothing new there, right? But when we do that, I need to kick electrons up onto our oxygen right here. So I'm going to asterisk that carbonyl carbon we just attacked, just so we kind of can stay organized and make sure we don't lose any carbons. Now let me draw my product. So I'm going to first draw my cyclohexane ring. And remember, we reformed the carbonyl. So I'm just going to fill him in right there. Now remember, I dotted my alpha carbon that we attacked with. And we made a bond from this alpha carbon to the carbonyl carbon in the substrate we attacked. So if I draw a bond, that is my asterisk carbon, right? So I'm going to asterisk him. And now let's fill in the pieces that he's bonded to, right? He now is attached to an O-, right? Because those electrons kicked up from the attack. And then straight off of him to the right, we have the benzene ring. So I can fill in that benzene ring. Okay. Now in the last step of this reaction, all we're going to do is pick up a proton for this oxygen right here. And since we're in a basic environment, that would just come from like water, okay? Because we don't have any hydronium around. So if I just drew water, you can always just kind of assume this is going to happen. I'm just kind of showing it to you guys to be completely transparent, right? So if I drew my arrow down, here's the final product of an aldol reaction. Just redrawing the product of the protonated alcohol. Okay, so like I said, this chapter is all about relationships, okay? And here's the relationship. If you do an aldol reaction, okay, and you don't add heat in, we'll do this with heat added in a second, this is the relationship you can expect. If I look at my carbonyl carbon, and I give him a count of 1, and then I count 2, and I count towards the carbon attached to the alcohol, you can see that they're 3 spaces away. We call this a 1,3 hydroxy carbonyl. Now, don't freak out if that word sounds big and scary and hard to pronounce. You know what this word means, right? 1,3-hydroxycarbonyl. That means that they have an alcohol, a hydroxyl group, and a carbonyl have a 1,3 relationship, right? So if you ever see maybe in a synthesis problem or maybe a complete the reaction problem, if they gave you a product and you need to give the reactants, if you see a carbonyl and an alcohol 3 spaces away from each other, chances are it was from an aldol reaction, okay? So this is the type of problem where, so this relationship is key. This is one thing you tuck in your back of your head and you need to remember during this chapter. Now, some other terminology. Because our enolate and our carbonyl were different from each other, this is called a hetero aldol reaction. If I were to use cyclohexanone to be my enolate and cyclohexanol to be my substrate, we would call that a homoaldol. Okay? So if you use your enolate with one thing and you attack that same carbonyl, it's called your homoaldol product. But if you use 2 different species, that would be your heteroaldol product. Okay, so let me erase this. I'll show you kind of what happens when we add heat, and I'll show you a homoaldol example. Okay, so let me, as I promised, let's do a homoaldol reaction together just so you can kind of see what that's like. And then I'll kind of show you guys what happens when you add heat in with an aldol reaction. So let's use this cyclohexanone, right? The enolate would look like this. Right? It's symmetrical. We don't have to worry about kinetic versus thermodynamic. And then let's just say, right, we make him an enolate. We're in basic conditions. And let's just say we're going to attack another cyclohexanone, right? So in the example previous, this was our enolate, but then we had benzaldehyde. But now we have the same species, right? One's just the carbonyl, the other one has flipped to the enolate. So I'm going to show you guys what happens when you add heat in to an aldol reaction, okay? So remember, we bond from the alpha carbon. So I'm going to take these electrons, swing them down to reform our carbonyl. I'm then going to take these electrons in the double bond, and they're going to come from our alpha carbon to the carbonyl carbon and make a bond. And these electrons swing up onto oxygen. Okay? Let's draw the result of the electron flow. Remember, I didn't touch, my carbonyl reforms, and that's the only thing that changed on this piece right here. Okay? And remember, I dotted this carbon, my alpha carbon, and I'll actually turn him into an asterisk. So one line from my dot carbon goes to my asterisk carbon, the one I bonded to, that partially positive carbonyl carbon we attacked. And he's attached to an O-, and he is one of a 6-membered ring, okay? So this is going to look weird. But 1, 2, 3, 4, 5, 6. Okay? I hope that makes sense. Okay, so here is what's weird about adding heat in. So again, you're going to pick up a proton from water, right? That doesn't change, like we did previously. So let me redraw that real quick. Didn't change the left half, only protonated the right half. Sorry, it's weird to draw a 6-membered ring that way. Okay, let me make sure. 1, 2, 3, 4, 5, 6. Sorry, it's a little ratchet. Okay, so here's the difference. Because we're adding heat in, something kind of changes. What's going to happen is we're going to kind of drive towards making a conjugated system. And we add enough heat in that we can actually drive off this OH. Normally not a good leaving group, but the heat allows us to kind of overcome that energetic unfavorableness, if that's a word. So what's going to happen is this. We're actually going to look at that same alpha carbon we attacked with, and if you have another alpha proton, here's what you do. Something's going to grab it. Let's just say, since we're in basic environment, let's just say OH-. He would grab an H. These electrons right here from the alpha protons, or the alpha hydrogen, swing down, and you're going to kick off OH. So it's kind of like a dehydration type move, right? You're kicking off kind of like water. Okay, so what happens and why this is a favorable thing, especially when we add the heat in to do it, is because if I add, or if I redraw my left half, right, nothing changed here, but from that alpha carbon yet again, now we have a double bond. And he's attached, right, this carbon right here, who's now part of the double bond, he's attached to the rest of a 6-membered ring. Oh boy. Hold on. Draw this. Okay. There we go. Okay. So here's kind of what happened. The reason why that was favorable is because if I can assign numbers 1, 2, 3, and 4, all of these carbons here are sp2, 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 right? We have a link of a p orbital, a p orbital, a p orbital, a p orbital. We have a 4-membered conjugated system, right? And we know conjugation is favorable. It allows for resonance. It allows for the delocalization of electrons. So, right, these electrons aren't static. They're constantly moving. This negative charge is kind of shared between this network of 4 atoms. So even though it was unfavorable to kick off OH minus, a bad leaving group, this heat allowed us to do it to then get to a more stable energetic product in the end. Okay, so again, you can see that we did an aldol reaction in the intermediate steps, because if you look right here, carbonyl is 1, this position would be 2, and the alcohol would be 3. So that would be our 1,3 hydroxycarbonyl. However, that obviously isn't in our final product. We have a new relationship. So if you can see, if you see this 1, 2, 3, 4 conjugated system, that is indicative of having what's called an aldol condensation, right? Because we said earlier that kicking off this OH minus as well as removing that H is a dehydration step. It's condensation. Also, here's kind of another word for, instead of saying 4-membered conjugated system, it doesn't exactly have a ring to it. You can call this functional group right here, you can call it what's termed an enone. And here's why. ONE for ketone, EN for alkene, right? So it's like an alkene runs right into a ketone. Okay? So there's plenty of practice for both regular aldol reactions without the condensation, as well as aldol reactions with the condensation. Remember, you have to have the heat for the condensation in basic conditions. I kind of highlight in this worksheet it has all the big reactions in it. This is the first reaction. So you guys can do the part of the worksheet that deals with aldol reactions in basic conditions after watching this video. In the next video, we're going to talk about aldol reactions in acidic conditions. And the best part is, if you understood this, you already understand the acidic condition part. See you in the next video.